Good afternoon, everyone. It is my pleasure to be the session chair this afternoon. And I just want to start by introducing our first speaker, who is Erik Frankforter. He is a research engineer in the Non-Destructive Evaluation Sciences branch at NASA Langley Research Center, and he is going to be talking about verification and validation this afternoon. Erik, take it away.
Okay, excellent. Well, good afternoon, everyone, and thank you for the introduction, Melissa. So for today, in this presentation, I'm looking to discuss the Elastodynamic simulation software that we've developed at NASA Langley Research Center and talk about verification validation from kind of a researcher's perspective, which has its own unique challenges in expertise, time constraints, technological readiness level, in a sense, it can be important to know how to navigate. In part of this, I'll be looking to give examples from software that we have developed, in-house software at NASA Langley Research Center, as well as software that has been open source. And from there, I guess I should start by acknowledging my co-authors. So Bill Schneck, Elizabeth Gregory, Cary, all also work at the Non-Destructive Evaluation Sciences branch. So for today's talk, I'm going to start with a little bit of background on the needs of non-destructive evaluation and the needs of computational non-destructive evaluation for NASA applications, verification and validation needs with a inclination towards lower TRL research software, and then some of the verification practices that we have found helpful for high-performance computing software and validation approaches for elastodynamic simulation. So
Erik,
a quick overview.
I just want to ask if you're changing your slides. We're not seeing them change.
Oh no, thank you very much. Thank you very much. For non-destructive evaluation for NASA, I wanted to give just a really brief overview here in terms of what people think of NASA. For ongoing missions, we have the International Space Station continually manned, but also the Space Launch System, a large rocket that is fundamental to the Artemis program for taking the next man and the first woman to the moon, as well as taking the information that's learned from that to help to a future mission to Mars. We also have things like the Lunar Orbiting Gateway, which is going to be an intermittently manned structure, which has a large pull from the NDE side for the need to be able to do on-demand monitoring or structural health monitoring for this. So from these sorts of applications, and really there's a large variety of missions that need NDE and NDE research, certain patterns tend to emerge. And this can be things like the need to inspect large areas, the use of advanced material systems, like carbon fiber reinforced polymers, like additive manufactured metals, even lithium metal batteries, which have material heterogeneity and isotropy that really challenges conventional heuristic methods of inspection. And this is where simulation comes in. In using simulation, we're able to take these complex, often high cost and low quantity parts, and to really take the understanding that we get from the simulation to be able to fill in the gaps for unique use cases. Even when you're talking about parts that are made in ones and twos, that can be hard to get a statistically representative sample just from empirical means. So for the branch, for my branch, I'm at the non-destructive evaluation sciences branch. So at NASA, across NASA centers, there's a variety of non-destructive evaluation, but in terms of research capabilities, this is the only branch level research. This is at NASA Langley in Hampton, and this involves things like the development of advanced NDE solutions, the use of cutting edge NDE techniques and technologies for challenging inspection scenarios, advanced material systems. My work here is falling primarily into physics-based modeling, and this is developing high-performance computing computational models, analytical models, testing them, showing that they are applicable for components, parts of interest, and to transition towards using these to guide inspection processes to understand the impacts of novel flaws or defect types. So when we're talking NDE simulation, here I'm really focusing in on elastodynamics, which is applicable to things like guided wave structural health monitoring or UT inspection. We're talking about elastic wave excitation, which would be ultrasonic transducer, maybe a bonded piezoelectric wafer, a pulse laser. That energy then propagates to the material. Through the material, the component interacts with the defect, and then upon scattering with the defect, that wave contains information relevant to that damage. Upon detection via transducer, maybe a laser vibrometer, a bonded sensor, then the interpretation of that data is really an inverse problem for the damage is encoded into that signal. So by using
Erik, I'm sorry to interrupt again, but we're still seeing slide 3.
Yep, just call out slide numbers and this should work.
Thank you so much.
Thank you.
I really appreciate it. So the in getting a verified and validated model, we're able to do things like providing insight into the underlying interaction phenomenon of the inspection, extract signal features that correlate with relevant inspection parameters, things like flaw size, location, even flaw geometry parameters, different flaw types. Enable consideration of NDE during the design stage. This is actually an ongoing challenge. Without the access of easy to implement validated tools, validated for the application at hand, then NDE is often considered last in the design stage, and some parts are very challenging to inspect or maybe uninspectable, which can be unfortunate to find out later down the road, as well as the developing methodologies for challenging inspections, otherwise intractable scenarios, and simulation can help to fill in this gap. So in this case, because of the time considerations, let's actually skip ahead to slide 7. Thank you. Okay, on slide 7. So when it comes to Elastodynamic simulation software, this is actually kind of an interesting scope to work in for research because there's a variety of applicable commercial tools already. And this is not an exhaustive list, but most of these are finite modeling tools. Many of you will already be familiar with these. We also have more custom high-speed tools like OnScale, Pogo, SIVA, and some of these may have applicability or domain or algorithmic restrictions that may make them faster, but limited to certain use cases at hand. So in motivated largely by speed considerations, actually, we have found that, for example, for modest size inspection scenarios, it can take many hours to days to run an individual scenario. So even just running convergence studies can take large amounts of time. So we have been working at the non-destructive evaluation sciences branch on developing high-performance computing tools. And on the right, I have different algorithms that we've employed. So we have the Elastodynamic finite integration technique, as well as staggered grid finite difference techniques, both a Lebedev grid, rotated staggered grid. The latter is what I have primarily been working on because it plays well with high levels of anisotropy or triclinic material with heterogeneous media. In high performance computing, we've developed cluster or MPI parallel applications for clusters, but also algorithms that in themselves have low memory footprints. And because of that, the algorithm themselves can be suitable for high speed. So that is in terms of NDE simulation, which is not as mature of a field as CFD, for example, we're still able to get 2 or 3 orders of magnitude speed ups compared to many commercial tools. On the right, I have 2 software packages that we've open sourced. We have solid wave simulation led by Elizabeth Gregory with the GPU accelerated elastodynamics, and PenNDE, no acronym there. It's meant to express the suitability of the modules for cross-cutting elements of NDE simulation. So for simulation software considerations, here I have effectively my ranked order list of what I'm looking for in assessing software, which is it needs to solve the physics, appropriate physics. It needs to be applicable to the domains that you need it to. And then how mature is it? Is it well documented? Is there verification, validation? If you're for API, if you're limited through interacting with the GUI, it can be self-limiting itself. And then you also have speed, high performance computing capabilities, and extensibility. So due to any one of these needs, that's where you can start to get into the need to extend with in-house or the use of open source software. And this provides other capabilities like improved testability, tailoring for emerging hardware. You often have to develop custom code, for example, for GPU application. This is balanced against the time, costs, risks of development. Slide 8, please. So for V&V, here I'm working off of the guidelines in the ASME solid mechanics V&V guide. So verification, determining that your model accurately represents the underlying mathematical model in the solution. Validation, determining the degree to which a model is accurate representation of a real world problem from the intended use cases. So often think of verification as the software functioning is the algorithm solving the underlying PDE that you think it is. And a validation is applicable to your particular model and problem case at hand. This involves gathering evidence of applicability specific to your use case, and often is perceived to be, or it's recommended to be done hierarchically. So you can proceed from a component level to a kind of individual component level to then linking components together into subsystems towards the system level. Here I have listed some of the guidelines, and actually at the bottom, one to emphasize for the software development application, which is actually where researchers can have a lot of trouble because I'm an engineer first, and software development is as needed to be able to perform my research appropriately. So we have the NASA software engineering requirements, which outline software practices, which can be beneficial for researchers. Slide 9, please. Thank you. So in what strong V&V practices provide, and I feel like I might be preaching to the choir here, so I don't want to spend too much time on that, but assurance of applicability, reliability, shareability, being able to extend, being able to push up your technological readiness level, your TRL, in use cases where there's still maybe some questions to the fundamental applicability of a given algorithm. For research software, we have characteristics where we can have small teams wearing multiple hats, maybe needing to take on multiple areas of expertise. Research results can be as relevant as software developed. Individual benchmarks or example cases can be what you're interested in. So then the need to develop even more robust software, there's a time pressure component to that, where you already have what you need to publish a paper. So then we know that repeatability, replicability, extensibility is important, but there is no near-term motivation in some cases, except for intrinsic motivation. Then in addressing this, so in addressing time pressures, we actually have, in many ways, when you see researchers doing things like command line debugging, having trouble with version control, often there's actually just a skill development component. And there are especially code verification practices that speed up the development process, that are self-catalyzing. The good software testing reduces debugging, improving your workflows. In terms of expertise requirements, we have the leveraging of culture, specialization, code review, mentorship in small teams, and contrasting priorities. That is an ongoing issue, the trade-off between traditional research metrics and how good is good enough equality and replicability. This is an ongoing challenge to address, but there's some progress. For example, being able to get publications with open source software journals that tag research software with a publication that intrinsically tie the two. So slide 11, please. Thank you. So going into software verification practices, these are things that we found at the NASB for HPC code development or simulation code development that has been helpful. And I've divided these up into different categories, but really there's a lot of overlap between these. And it is not to say for researchers who are advancing in this to pick these up all at once, but to find a few that are helpful and again self-catalyzing. So that's things like the use of version control software to keep track, and even the use of version control workflows can be very helpful, and that can provide a structure and a framework to put good software practices around. The use of code reviews, which can allow for mentorship with people who have more experience, specialization in different aspects of code development, and testing. And if you don't test it, it's always right? The tongue-in-cheek there, but it's the testing helps you to provide assurances that it's working, and actually over time reduces the technical risk, the technical debt. In terms of documentation, I can't count the number of times that I've had to ask for how to install something, but instead of writing that email to say, yeah, this is how you should install it, you can write an installation guide one time, and then in incorporating practices like that, you find that your development processes in a team go a lot faster. Next slide, please. Thank you. So here I have just a simple Git workflow in terms of the feature branch model. So typically you go from a master branch when you go to a development branch. When you go back from development to master, you call that a version number increment. And then if you need to develop something, you spawn off a feature branch. And we find that you write tests as you develop your features. And then upon the merge back from a feature to a development branch, that's when you can incorporate practices like code review, even a CI/CD for automated testing, and in a sense, building your culture around specific agreed upon workflows to offload some of the cognitive load of trying to keep good code V&V practices. Next slide, please. So I'm going to go through this quickly due to time considerations. So for software testing on the right, I have an example from a C++, one of our open source GPU accelerated codes for 3D elastodynamic simulation. And the idea here is that you really want to use the testing framework, and you want your tests to be short and self-descriptive whenever possible. And then upon using these tests, various types of testing, then you have the intrinsic benefits to testable code, but also the ability to port from system to system, and it helps when you start to modify or extend these codes to make sure that your expected behaviors are still being encapsulated. So let's go ahead and skip to slide 15, please. Or actually 16 here. So I wanted to actually start with the validation practices, kind of a simple case, because I think it actually encapsulates a lot of good lessons that we have learned from this. I would call this battery fit, which is a bit tongue-in-cheek for the name. It's the elastodynamic finite integration technique applied for lithium metal battery applications. So we made a portmanteau of the two and the name stuck. This is a time-explicit second-order leapfrog technique, and here this was important for us actually in transitioning to our 3D models because it implies a heterogeneous scheme for the interface and boundary conditions. That's rather than explicitly specifying a boundary condition, it's encoded by specifying equivalent media properties, and here an effective density. That implicitly encodes the boundary conditions. So then we need to validate the individual propagation characteristics for wave propagation through layered media for the inspection within individual components and for boundaries. Next slide, please. Thank you. So here I have the full set of the full set of validation cases that we did for this. And this one is kind of an interesting case because we developed this code during COVID when we did not have any lab access at all. And actually, in a way, it actually worked out for the validation because for this sort of setting where we have low risk, it's not a safety critical application at this stage. This is just for research applications. It is very much time bound. We're able to do kind of a transitive validation where we have kind of a legacy of well-established theories in elastodynamics and in strongly tying to characteristics of those theories. Then we're able to say, well, those approaches and theories have been validated. Now our 1D case can be strongly tied to that. So that's bulk wave speed for an individual media, traction free boundaries, things like total internal reflection off of the free boundary, phase shifts after reflection, velocity characteristics of free boundaries, and then bimaterial interfaces where you have certain transmission reflection coefficients, phase reversals in certain conditions, and actually able to demonstrate conservation of energy and momentum throughout a given kind of multi-material simulation. So slide 18, please. Thank you. So for kind of just a select validation case here, we use the pressure wave speed in aluminum 5052. This is an alloy that's commonly used in lithium-ion batteries. And we have, I think one of the nice things about this is by tracking the propagation of the wave field over time, we're able to compared to a well-known theoretical bulk wave speed, and actually show that we can get a correspondence and convergence towards this value to within numerical error, depending on discretization. And actually, with the simple case, you're actually able to show that for all of these cases at hand. Slide 19, please. Thank you. So for the bimaterial interface case, this is from low to high impedance materials, from copper to aluminum. We're looking at transmission reflection coefficients. So on the right, we have incident wave on top, and then reflected wave on the left and a transmitted wave on the right. And using an L2 norm, we're able to calculate shape residuals, relative amplitudes, and a phase shift built in for certain reflection conditions. And again, able to show convergence within really numerical error to certain cases. So I think these are actually pretty neat cases to go through. One of the interesting things about this is these cases and these lessons are actually directly transferable to 3D simulation cases. There are certain assumptions that are built into the 1D model, like a single wave, either pressure or shear, a normal incidence wave going through planar layers. And if you actually create that condition in your 3D model, these cases work out of the box. They just take a lot longer to run. So I find that transferability is actually very valuable. Slide 20, please.
Erik, this is a 2-minute warning, okay?
Thank you, and thank you for bearing with me, and I guess extending due to the tech issues there. So in slide 20, so for 3D elastodynamic simulation software, and this is actually something we found for the various algorithms that I discussed earlier, the EFIT and the two finite difference algorithms, you start getting these different levels of complexity in geometric manifolds, faces, edges, corners, different types of boundary and interface conditions, especially traction-free boundaries, fluid-solid boundaries, and then the degree of anisotropy, whether it's just isotropic material all the way to triclinic anisotropy. And we find that we can actually have, we don't have enough time to test all the combinations here, but there are combinations that can actually break some of the algorithms at hand that we've tested. And that was kind of one of my lessons learned going through some of this essay back in my postdoc days, was finding what combinations of these will challenge during kind of a stress test of your algorithm. Go to slide 21, please. So, and in this case, we're actually looking at guided wave propagation. So these are kind of flat plate models with looking at waves that are guided along free surfaces, propagating lateral to the plate. We have laser Doppler vibrometry comparisons for analytical validations, and then we use a 3D FFT to extract, go from time, space to frequency wave number data. The wave numbers have analytical relations for guided wave modes, and here we have some examples of just the, we can get very close correspondence with the theory to the analytical model, still needing some model calibration when getting to the experiment. And slide 22 here, and I think this will be one of my last slides. We have here, I have a demonstration of a benchmark case, which we have a delamination placed between two plies in the carbon fiber reinforced polymer. And then slide 23, an example of the propagating wave field. So actually on that left figure, if you click the play button on that, so we can see the wave field emerging from the right-hand side with the transducer, propagating over to delamination. And you can see this kind of a reduction in wavelength here, where it hits that delamination, and then that reduction in wavelength is creating a kind of a damage-associated wave load that's associated with the two plies of the delamination. And we're seeing that in the dispersion curve on the right-hand side. On the bottom right, we have the frequency versus the wave number. we're seeing the left and right propagating values here, and these were corresponding to the pristine on the lower one, and the top is the damage associated wave mode. Slide 24, and then I'll one thing I kind of wanted to stress out of this is in the hierarchical testing, what we found in different simulation algorithms for the 3D simulation, and the combinations of conditions that are can really stress your algorithms. We have found that just starting from hierarchical bottom-up testing at lower technological readiness levels, when you don't know if your algorithm is going to work, can actually lead to a lot of disappointment and time expenditure invested into an algorithm. So here I have 3 examples of kind of some stress tests that we found useful. On the left, we have a triclinic media Langley propagation, which actually, when combined with traction-free boundaries in the EFIT algorithm, produced numerical instability. In the center one, if you're able to click that one, there's a monoclinic triclinic interface, which produced instabilities in EFIT and was unstable in the Lebedev finite difference scheme until we applied a interface scheme which required a planar interface assumption. Well, that actually didn't work for the simulation use cases that we have. So we had to switch over to a rotated staggered grid scheme, which lifts that planar interface assumption. And then the right-hand one, we have propagation, a video of a propagation circumferentially around a pipe. Here we're showing a 2D cross-section 3D algorithm here. This is the rotated staggered grid, and this one only worked in the rotated staggered grid scheme, would not be suitable with other published algorithms like EFIT, Lebedev. You wouldn't necessarily be able to replicate this with LISA or some of the other algorithms in the literature. So this is actually not a verification because we would have had to have used something like there are methods for like a method of manufactured solutions for analytically creating a solution and testing that the derivatives are solved suitably. This is a bit of a step below the verification. This is just a stress test, but we find that even when it's very difficult to have an analytical solution, just employing one of these, it's pretty quick to do, but also can provide a means to completely veer off of an unsuitable simulation algorithm approach. On 25, I have conclusions, and just to reiterate a bit, not letting great be the enemy of good in gradual advancement of research software verification practices, leveraging culture, group dynamics to overcome activation energy. We use the V&V of simple 1D approaches, kind of through this transitive approach to linking it to really well-established models, especially when there are resource constraints and time limitations, and these can be applied to the more complex 3D approaches. And the interspersing of stress testing when it is unclear if your algorithm is going to be suitable. It can be good to really find cases that challenge the applicability of your algorithm upfront. And that's all that I have. I don't know if there's any time for questions remaining.
I don't think we have time for questions, but if anyone does have questions, please, you can either put them in the chat and I can make sure Erik sees them, or you can get in touch with him directly. I believe his contact information is in the agenda, the DataWorks agenda on the website. Thank you very much, Erik, for that presentation. Sorry for all of the issues, but it worked out well. Thank you very much.
All right, thank you, Melissa.
Okay, now we're going to move on to Andrew Cary, who is a technical fellow of the Boeing Company in CFD and is the focal for the BCFD solver. He's going to talk about challenges in verification and validation of CFD in industrial aerospace applications this afternoon. Go ahead and take it away, Andrew. Thank you.
Okay, so yes, thank you, Melissa. And I'm going to be a very appropriate follow-up to Erik's presentation because I'm going to be using the same definitions for verification and validation. But I'm going to talk about a few of the challenges that I've run into in trying to apply verification and validation to different applications of industrial CFD. So repeating the definitions, verification is really the steps that you take to make sure that you've not only coded the algorithm properly, but that your numerical solution is also correct. And I've sort of split that out into three categories, and this is somewhat following the IIAA updated standard that was published as a technical paper, this 2016 3811, and is still working its way through the standards process. But basically, there's a code verification standpoint where really this is focused on the developer to ensure that the numerical algorithms are coded properly and that we get the right steps. And this is often associated with either the having analytical solutions or method of manufactured solutions as a way to just verify that everything is coded properly and converges properly per what you would expect from the algorithm. The next step is really solution verification. And this in many ways gets pushed to the responsibility of the user to make sure that for the particular problems of interest that we understand what the numerical errors are that are going to be associated with that particular solution. And so that this may involve things like grid convergence studies or looking at sensitivities of different parameters, but everything is really targeted at for a relevant application, trying to find ways to estimate what that numerical error is. And there are some references that also will talk about reviewing all the code inputs for correctness, which obviously if you have a incorrect input can lead to a zero order error. So for example, you have to make sure that your geometry is correct and that your flight conditions are correct in terms of CFD, just to make sure that there is no zero order error that goes on that will not go away as you refine the mesh. Another aspect which Erik touched on is code regression. And this is basically making sure that we have the appropriate software practices in place to ensure that once we have developed and tested software that it still remains valid for particular unit problems. Validation, on the other hand, is really the process of determining how well this model represents the real world. So verification is focused on the implementation, the numerical implementation, and making sure that that's consistent with the model, whereas validation is really that step of saying, does this model make any sense? And I want to emphasize a couple of aspects of this definition because it's a matter of determining the degree to which the model is an accurate representation of the real world. So that's how well does the model, whatever that model might be, represent what actually goes on. But it also has this important clause from the perspective of the intended uses of the model. So we got to make sure that as we utilize a particular model that we've actually are looking at it with respect to how we care about it. So for example, we may have a model that works very well for predicting drag, but because of some simplifications, it may not work well for predicting pressure at a particular location. And so we've got a lot of different things that are involved in pulling this together. Another aspect, which is a term that I've started using, is trying to refer to benchmarking. And I'm using this specifically in the context of when we are co-plotting experiments with simulations, because traditionally, we've often, in the CFD realm at least, referred to that as validation. And I'm going to draw a few distinctions later that's really just the first step, and there's additional steps that are necessary if you really want to say that you are doing validation. I will point out that while ASME and AIAA both agree on these definitions in terms of, we call it numerical science, there are other disciplines that do not use these terms consistently with this particular set of definition. They have got their own definitions and with appropriate rationale for those. So sometimes that's one of the areas that we always have to cover, is making sure that people are interpreting words the same way. So why is this really important? And I've broken these down into a couple of steps. And code verification is what we've sort of started to introduce. And this is making sure that the equations are solved correctly. And so obviously we need to do this just to make sure that we believe that that's the case, especially as a code developer. Users will typically presume that that's taken place. Solution verification, as I've already indicated, is the responsibility of the user, because this is how we start to develop estimates for numerical certainties that should be applied to later data. Validation is then the next step, where we're actually trying to compare how good that model is so we can get an estimate of model form uncertainty. And when you combine these three steps, we're trying to get to predictive capability, because typically we're not going to just run CFD on a case where we already have experimental data. We're running it for the purpose of gaining additional insight, or we're trying to apply it to a different case that's in some ways close to the one where we're using for validation. And so that's the predictive capability in mind. And so by building up through code verification, solution verification, and validation, we try to get to the place where we can actually establish confidence in the answers that we would get from new problems. So as a simple example, this is actually a problem I give to my students in a CFD class I teach, is we compute the temperature distribution on a uniform square plate, and we'll just use a elliptic problem. We'll use a real simple 4-point scheme, and it should be second order. And lo and behold, if we have a second order curve with respect to our grid spacing, we see that this behaves very close to second order accurate. And so this seems like its verification should be a straightforward, easy situation, no problems at all to worry about. And this is all contingent really upon some of the ideas behind Richardson Extrapolation, which assumes that we've got smooth solutions and uniform, or at least consistent, grid refinement, asymptotic, that we're in the asymptotic region of the solution convergence, and that we have a consistent scheme. So in those situations, Richardson Extrapolation tends to work very well. But if we take it into problems that don't necessarily fit that exactly, we start to see that there are challenges. So this goes back to an example now 8 years old of looking at this simple inviscid channel with just a simple bump, and it's entirely subsonic with a free stream Mach number of 0.5 and a maximum Mach number of almost 0.8. And essentially, in this case, it should be completely isentropic. The governing equations, there's nothing there to introduce anisotropy, or I'm sorry, nothing there to introduce a entropy generation. But when we start looking at results for the L2 norm of entropy, we've got first order reference curve, second order reference curve, and third order reference curve. And we see that many of the codes that are supposed to be second order behave second order, but some of them, for example, this purple one with the blue dots, which happens to be CFD++, or this blue with pluses, which happens to be BCFD, both are more like first order behaviors. And that, of course, begs the question, well, why is that? Well, at least with BCFD, I can confirm that the reason is because it's using a first order inviscid wall boundary condition. And that ends up generating entropy and makes the overall prediction go from second order to first order. And that's exactly what the theory would suggest should happen. And so that begs the question. All right, so that means that this is formally a first order verification that we've performed, at least in those cases with a first order wall boundary condition. what does that mean? Does that mean that we've verified this because it didn't give us what we wanted? And the answer is formally no, but it may be that we don't care, because if we don't run if we know that the problem is associated with the first order inviscid wall boundary conditions, but we never run with an inviscid wall boundary condition, then it doesn't really matter in practical applications. The interesting thing as well is that if you look at other metrics, for example, the drag coefficient, or even point-wise values, you'll see that you get different convergence rates. And again, this is not contradictory to theory, but it often goes beyond what people are introduced to. And so, for example, we see that the drag error is almost third order accurate for these cases that were second order accurate in terms of entropy, because of the way that we're combining the output into functionals. Similarly, if you look at the point values, though, you'll see that depending on where you sample, you end up getting different convergence rates. So this just starts to open the question and make us recognize that what we thought was a simple case, or we could convince ourselves might be a simple case, is actually a much more challenging example than first blush would indicate. Another example is also looking at boundary conditions. It comes from the turbulence modeling resource. And this specifically goes back to a case that was referred to as the near wake case that was used for a verification study for the third high lift prediction workshop. And this particular case was acknowledged that the far field boundary was close, but that wasn't believed to show any instances or any problems. And if you look at, for example, the pressure drag coefficient, using Fun3D and CFL3D, they come in very nicely to the same answer, as does BCFD with this hold state condition. However, the far field boundary condition is only specified as being characteristic based, and that leads to some ambiguity. And we actually originally had implemented a different characteristics boundary condition that you can see goes to a very different drag level. And it's even more exacerbated if you look at the lift coefficient. Now, the scale is somewhat zoomed in this case, but you can see that there are some pretty significant differences that take place, in this case, due to the detailed implementation of the boundary condition. And so a lot of times when we're trying to compare to other solutions, or possibly even to analytical data, we may find that the boundary conditions are not implemented entirely consistently. And although they qualify as the right type of boundary condition, there may be differences that end up leading to some of these problems, where you would tend to say, okay, this is not verified, there's something wrong. And in terms of the case on the turbulence modeling resource, they've subsequently expanded the far field boundary, and agreement has now been obtained with a much wider range of boundary condition specifications. So this was a case where, by expanding the grid and making it so that the boundary condition that was not intended to play a role did not play a role, things worked out much better. Another case is now looking actually at the interior scheme. And so I ended up taking and generated a oblique shock for a supersonic flow, and went through a variety of different rotations of this grid, looking at how the scheme represented things under these different rotations. And looking at the convergence, you'll actually see that most of the L infinity norms actually diverge. And this is for HLLE, HLLC, and row scheme, all schemes that we use on a very regular basis. And even the discretization error ends up showing, in general, that it's 0th order accurate. Well, what's going on in this case is that because the discontinuity exists, by the formal definition of consistency, these schemes actually are inconsistent in the presence of shocks, because they added these stabilizing terms, which we need for robustness, but they actually in those exact situations are not consistent with the original equations because they've added exactly that dissipation term. And so this is sort of a artificial case where we've demonstrated through a wide range of grid refinement in this 2D box that took all the way up to 10 million cells, that they are independent of rotation, or essentially independent of rotation, but you do have this problem, or this perceived problem, with the scheme not working the way you'd expected it. If we start moving towards validation, this is looking at a backward-facing step, also from the turbulence modeling resource. And the blue dots represent the grid family that's on the resource website. And then we've continued that refinement all the way from 1.3 million cells up to 8.2 million cells. And in this case, you can see that the drag continues to converge nicely. And so we might expect that this grid family is well on its way to being grid converged. But if you look at the separate reattachment point, you see that right at where that last grid family stopped, at least BCFD predicts there's a shift that takes place before it starts reconverging to a presumably different answer. And in this case, we can actually see that what's happening is we're adding an additional vortex or separation right at the corner of the backwards facing step. And so that's changing the final reattachment point. And so as we keep adding more details to the flow, we're causing this global change in behavior. And so this is, again, a violation of some of those assumptions that went into the Richardson's analysis. And that's why things don't behave the way we expected it to. If you look at this case as a validation case, the experimental error is this magenta error bars of 6.26 inches plus or minus 0.01 inches. And if we apply a uncertainty quantification, looking at both the grid resolution and confidence in turbulence model coefficients for the SA turbulence model, we end up at this LXX grid of getting to be a uncertainty, which does encompass the experimental value. And if we go one level of grid finer, you see that we're right about the edge of the experimental uncertainty. And so by the time we would add on additional uncertainty due to the turbulence model and grid resolution, we would see that that would probably still at least overlap part of the experiment. And so that would tend to lead us towards the indication that there is a level of suggestion that says that the CFD and the experiment do agree in terms of validation. And that can be quantified a little bit more specifically using an area validation metric. As a final example, I want to look at the high-speed CRM. So this is actually the configuration used for the drag prediction workshop. And we've assessed the cruise drag specifically at a lift coefficient of 0.5. We've run both the workshop family of grids and some alternate families of grids. And so this is the sequence of work that we did to try to get our solution verification. And so that gave us an estimate of the numerical discretization error. We then looked at input uncertainties based on the experimental conditions. So because it was a well-defined experiment, there's fairly small uncertainties in the experimental conditions. And we included those same uncertainties that we'd previously investigated for turbulence model closure coefficients, particularly the von Karman constant, sigma, which is associated with the diffusivity, and CW3, which is one of the other constants in this Blard-Mars turbulence model. And when we did that, we ended up seeing that we had a series of different uncertainties that stack on top of each other. We've assumed that these are linearly, that they are statistically independent of each other, and so we can just add them. But if you look at it, so this black curve represents the aleatory uncertainty due to our input conditions. And it says that our drag is probably somewhere between 270 and 273 counts. Once we add on the uncertainties due to turbulence model, that gives us the blue offsets. And now we have a probability box that starts to describe our level of confidence that we have in the solution. And it starts to say that no, maybe when we allow for that, we could go as low as 267 or as high as maybe 273 based on our uncertainty associated with the turbulence model. And then once we add on finally our uncertainty due to this particular level of grid resolution, we see that it actually gives us a much broader range of uncertainty, possibly as low as 260 and possibly as high as somewhere around 276 or 277, just depending on how you interpret the P box. To do the validation, we need to compare this to experimental data. And so we pulled out data from a couple of different entries, some in both the NTF and also in the Ames 11-foot tunnel. And plotting the experimental data also as a P box, considering the experimental uncertainty and then just the variation that they had due to repeat runs, we end up getting this comparison. And you can see that there is a significant, there is complete agreement or almost complete agreement between the experiment and the simulation based on this upper series of tests, which happens to correspond to the Ames test, but we do fall a little high in terms of drag, and so there is a level of disagreement with the experiment that actually turns out to be from the NTF. And the ultimate reason for this is that there was not some aeroelastic deformation in the analysis that was ultimately determined to exist in the experiment. And so there was some differences that we had not accounted for, and that should have further widened our probability box to give us more confidence in determining what the model form error, how much we can trust the CFD compared to experiment. So
Andrew,
just in, yes.
Andrew, I just want to give you a 5-minute warning, okay?
All right, I should be good, thank you. So to encompass where we are really with verification and validation, what does it really require to accomplish these, particularly in my field of CFD? And in summary, I'll say, first of all, attention to detail. There's always a lot more going on than you would expect at first glance. And I've yet to do a verification or a validation test with my code that went as smoothly as one would ever expect it should, as some of those earlier examples illustrated. It's important to include the uncertainties and sensitivities in the analysis, whether that's the discretization errors, the model uncertainties, as well as the boundary conditions and geometric uncertainties, because those are ultimately what you're trying to gauge as you start to build up your P box. And then lastly, you need to have experimental data with additional measurements to anchor the simulation. So you got to recognize that we really need to do validation studies for this purpose, as opposed to standard engineering test entries. And so that in particular means that there's a more focused effort on redundant measurements, tighter controls, and repeat experiments. I will also point out that per the definition, validation does not indicate that a particular result is fit for use. It just tells you the level of agreement that takes place. It is still up to the engineer to determine, given that level of agreement and the similarity of my use case to the validation data, is this something that I can go ahead and apply and have confidence in? So as my last chart, I'll say, repeat again, verification is much harder than one would expect. I've done both comparison analytical solutions, I've done method of manufactured solutions, and every time we do that, we do find interesting aspects that we have to take a look at. And I will reiterate for all the users out there, solution verification really should not be overlooked, because that's how you start to determine estimates for the numerical uncertainty that's relevant for the particular problem that you're doing. And then with validation, codes are not validated. That's an important thing I used to say, and many people used to say, but we need to be a little bit more precise with that, because we can only validate a particular process applied to a particular study with a given end result in mind. And that's how we develop the confidence that we can trust the results. And we will need to include uncertainty quantification with the CFD results as we try to do this validation. And this actually sets up the next talk fairly well, because one of the things that is important there is really making sure that we do establish this confidence in the CFD results. And so these are the steps, the very meticulous and detailed steps that need to be taken to build that level of confidence. And I'll stop there, Melissa.
Thank you very much, Andrew. I have a couple of questions, but I don't think we really have time. I will ask just one question. Let's see. You say here on your last slide that we need quality validation experiments. What do you mean by quality validation experiments?
So
just that we also
need
to have uncertainty and all the measurements we can get?
And I'd say that everything is well defined, which falls into the additional measurements. But if you actually, Bill Overkamp and a couple other authors that he's worked with has talked about what a validation experiment really means. And so that's the real focus, because a lot of times we'll do engineering experiments and then try to use CFD to validate against that. That just leaves us shorthanded.
Right. Yeah. And I think that's a very important point to bring out. So thank you very much. If anyone else has any questions for Andrew, please either put them in the chat, or you can find his contact information, I believe, on the DataWorks website. Thank you very much, Andrew.
Thank you.
Now we'll move on to the third and final talk in this session. And this is going to be presented by Timothy Mauery, who has been involved for the last 20 years in the development of low-speed CFD design processes. He has had the opportunity to interact with users and provide CFD support and training throughout the product development cycle. And with that said, he's going to be discussing certification by analysis. Okay, and you can take it away, Timothy.
Great, thank you, Melissa. This talk is going to be considerably less technical, I think, than others, as far as talking about a vision for virtual flight and engine testing. And most of this presentation was supported by a NASA Langley contract. And so it was a fairly large team of people. It's a 2-year study, and it was made up of experienced members of the aerospace community, both in the airplane and engine manufacturing sector, as well as university researchers. We had a technical advisory committee or team that was comprised of subject matter experts and high-level managers from both Boeing and from Pratt and Whitney. So that's kind of out of the way. So today I'm going to talk about the challenges of certification, how analysis can be used in certification, and just sort of some background information about that for people who may not be as closely tied into airplane certification. And then I'll cover some of the elements of the project that led us to our conclusions, and then some of the results and recommendations that we had for that came out of this study. So just a quick overview of the certification flight testing process. This process begins long before an airplane is actually built. It starts actually before the airplane is defined. Some of the standards and certification bases are determined sort of concurrently with the airplane definition. And so if you want to insert a particular analysis capability or a different means of compliance, then that needs to be known pretty far upstream, because then you're going to develop this capability, put it into some process, go to the regulatory agencies, figure out how they're gonna, if they're gonna agree with it, or if they're not, there need to be some additional modifications to that process. And then after they've agreed with that particular process, then you have to do the analysis and show compliance to the various regulations. So that capability is needed quite a bit upstream. So there are approximately 1,800 airplane-related regulations and about 200 more engine-related regulations, as well as some others that aren't listed directly here. Lots of, more regulations than we could possibly put together in one 2-year study. And so we've narrowed it down. We narrowed the scope of this project down by focusing on part 25 subpart B, which is flight, and part 33 subpart F, which is aircraft engines block testing. And we chose these two mainly because this is where a majority of the full-scale testing occurs. Full-scale engine testing, such as blade out, where you actually have to destroy an engine article by, throwing, by losing on purpose a fan blade into the engine while it's running. And then in flight, this is where you see all of those, videos online, which I encourage you to go look at, about maximum energy braking, or VMU testing, or crosswind takeoff and landing. And so there's, we had to narrow it down to just part of this. And even so, we came up with about 60 different flight maneuvers and tests that that would need to be addressed in some way. And so as part of this, we kind of chose some representative cases, and I'll talk a little bit more about those later. So I guess the first thing that we'd like to I'd like to cover is, what is certification by analysis? What do we mean by that? And that refers to any alternative means of compliance with those standards that we talked about earlier that are in lieu of physical testing. And so that could be, subscale wind tunnel modeling, numerical methods, or simulation methods, anything that's not a direct full-scale flight test. And so why is this, why should we do this? So physical flight testing obviously is a complex and time-consuming endeavor. It can last, up to a year for a new airplane, and that schedule is constrained by a lot of external factors, such as suitable weather conditions, equipment availability, crew availability, and so a lot of those, moving to analysis would sort of take the flight testing aspect of certification off the critical path. That's something that could be done a little bit further upstream. And even a partial elimination of testing, we don't anticipate that, for quite a while, that we're going to be, using analysis to completely replace flight testing. But even a partial elimination can streamline that process, reduce the logistical requirements, and reduce the costs of certification. Sort of a side benefit of having analysis that's at the level of accuracy as for certification is that you can catch performance surprises and issues that you see, downstream in the testing cycle a little earlier on, where they can be corrected without as much cost or time constraints. And it can be used to support concept and early configuration development that can offer improved efficiency and performance. And that benefits everybody. That benefits the flying public, it benefits airlines, and it benefits the manufacturers who can get their products to market more quickly. And so this, this is a far-reaching goal that is beyond just certification. So why haven't we done it already? It's because it's a hard problem. Certification is put into place to ensure product safety. We want passengers, crew, and equipment to arrive home safely after every flight. And so there's this high standard for compliance substantiation. One of the key elements of this certification outside of flight testing is in Part 25, Section 21, which states that the analysis method has to be equal in accuracy to the testing. And so we need to make sure that we have tools that are not only accurate, but also that we can demonstrate how accurate they are. And right now, you can see in these charts that the current limits of CFD are really, it's really limited to this 1G design sort of region. And a lot of the tests happen at the edges of the envelope because that's where, if things go bad, it can be kind of a problem. And so, it's also difficult because, to be able to put these sorts of technology to validate it, to validate the application of technology, it takes a lot of time and it takes a lot of resources as far as, simulation and storage. And historically, we've kind of just looked at sort of single point sorts of analyses, and we're going to have to start moving to this system level sort of multidisciplinary analysis paradigm. So at the beginning of this year, the beginning of last year in January of 2020, we invited several hundred members of the aerospace community to participate in a survey. And we got about a third of those responses back, about 120, and from a wide variety of backgrounds and expertise. And the survey was comprised of questions regarding several aspects of certification by analysis, specifically about the impediments and roadblocks, as well as considerations about the future, just because those are the things that we need to really work on. And so we found that the top technical impediments were physics modeling, confidence, and then system integration. One, I guess, optimistic note is that most people thought that we could eliminate about half of the testing that we have that we have to do now if we could overcome all of the impediments that we currently face. So we took those responses and we hosted a workshop later in the year in July of 2020, and we took those topics, kind of formalized, using the input from the survey, and we decided to talk about technology development, system level integration, and then some confidence tools, verification, validation, and uncertainty quantification. And so during that time, we also presented some initial roadmap concepts, and through input from the workshop, we were able to refine that roadmap. So after gathering all the information from the roadmap exercises and the survey and the workshop, we came up with sort of a vision for certification by analysis over the next 20 years. And it has 4 key elements. The first is obvious. That means that, it's just basically we have to be able to have reliable prediction of aerodynamic performance throughout the design envelope. And especially in maneuvers and analysis cases that are important to airplane certification, and those tend to be rather complicated. The second element is that we need to be able to increase our level of usage with appropriate uncertainty quantification and other confidence tools for airplane related products. Third is that we need to have some rigorous validation of real airplane type data and some full-scale airplane and engine testing. And then the fourth aspect is looking even more to the future, and that would be that initially we can synthesize flight test data, ground-based wind tunnel model data, numerical simulation with data fusion methods to increase the fidelity of our databases in flight simulators. But later on, we would like to be able to use modeling to define the operational characteristics of the simulator, and just using testing to validate our simulation. So that will probably involve machine learning and some AI techniques to be able to just manage this large amount of data that will be generated. So based on the vision, we developed an integrated framework that will help to provide a measured approach through incremental efforts that build in complexity. So, the technology development is sort of the fundamental research things that people are doing, scale resolving methods or adaptive mesh refinement. And then those feed into predictive capabilities that are sort of integrated implementations of technology. They're more than just an application, more than just a technology, but it's a technology that's usable to do things that such as CL max prediction with icing or fluid structure coupling. So it's more than a technology, but less than a particular certification type application. And so then these applications are kind of the end goals that we have when we're developing these capabilities and technology. So we went through several iterations. I think it was around 25 of this roadmap, adding and removing elements. And it's a little more complicated than the Vision 2030 CFD roadmap. And that's because it involves more than just CFD. It's not a short-term sort of a goal. It's going to require concerted effort and resources over the next few decades. And so a long-term roadmap is needed so that we can effectively prioritize our resources. And you can't really necessarily see it, partly because of the size, but verification, validation, and uncertainty quantification will be inserted and apply throughout this entire framework. So I'll blow it up a little bit so that you can see sort of the different chunks of this map. So we grabbed just a few of those 60 validation, or sorry, 60 of those certification applications that came from the regulations. And we sort of put them in a progression of capability according to their complexity. So sort of short term, these are things that, as we talked with our EUM community, which is they work with the FAA as far as certification goes. And so we involved them to understand what required elements of testing are now and what some potential analysis approaches might be. So there's a short-term sort of 5-year application, and then there's a mid-term, maybe 10 years out, and then long-term. And these are, obviously the big problems that we really want to be able to solve, because those are the ones that are either a more dangerous type of test or a longer, more difficult sort of test where the difficulty sometimes causes repeats because of the difficulty of acquiring quality data. So the next chunk, I guess, is the predictive capabilities section. And these are sort of sub applications that feed into the primary cert by analysis application. And we divided this again into sort of 2 parts, the engine part and the airplane part. And then on the left shows increasing complexity, where you have some single discipline analysis that you can set up, and then some multidisciplinary coupling of maybe more than one field, but it still is less than what's required for the certification application, and then some larger full system type capabilities where the entire engine combustor compression model needs to be, we need to have some way to model that so that we can go into various applications such as operability at sea level and altitude. So the triangles represent engine capabilities, and the circles represent the airplane capabilities. So the fundamental technologies that are this sort of is more familiar as far as if you're familiar with the CFD Vision 2030 roadmap, where you have this progression of capability or progression of technology that allows you to see kind of when it will be ready. And we've chosen that this sort of yellow color means that it's ready for some initial applications that we've got an initial ability to apply that to something more complex, and then the green points mean that it's production level or ready for more general usage. And you'll see that there's a swim lane or a row that specifically addresses UQ, and some of the technology development that's required to improve our uncertainty quantification, and how that can relate to other confidence tools. So these solution confidence tools are really, they're crucial as being able to convince the FAA or other regulatory agencies that we know what we're talking about, and that we can provide answers that are just as accurate as the flight test results. And as Andrew mentioned a little bit before, there's a fair amount of complexity that goes into even just defining various terms and showing how they fit into this solution confidence environment. So one of the ideas that we propose, or that has been proposed, is a validation domain, meaning that you where you actually have experimental data, and within the domain, if you have points that's shown by like the C's in this blue region, those are computational results and they're not directly validated. So there's going to be some interpolation, and we have a fair amount of confidence in interpolation, but we aren't going to be able to validate every single point where we need computational results. And so we're going to have to figure out how to extrapolate the validation domain to the applications in the regions that we want it to be applied. And so there's a fair amount of work that needs to be done as far as solution confidence tools go. So we have some recommendations, and we need the concerted investment of more than just one group to be able to reach these SERP analysis goals. They're kind of too large to be tackled individually. So we'll need to collaborate, and it has benefits for not just industry. Obviously those are easier to quantify, but it also gives research organizations like NASA their technology development and provide substantiation as to why the things they're working are important, because they actually do apply to real world aerospace problems. And we also we need to keep the regulators involved because they're ultimately the ones who are going to put their stamp of approval on it as a certified airplane. So we've come up with some recommendations for NASA, and these are pretty straightforward, the kind of thing that you might expect. We want to build on the current projects that are based on that are working towards fundamental technologies like scale resolving methods or dynamic automated mesh refinement. So that one's kind of just keep going down the path that you're going. We think that's something good for NASA to continue doing that. And then number two is we want to extend beyond just the normal aeroelastics, aeroacoustics that we've kind of collaborated on in the past. We want, NASA has some unique capabilities that will allow them to look into the more complex problems like aeroservo elasticity with pilot interaction during a post-stall maneuver. And so we need to accelerate the development of these multidisciplinary capabilities. Number three is some validation capabilities. The CRM ecosystem is a good start for being able to develop these new multidisciplinary validation methodologies. But we also want to have some dynamic, maneuver-based validation, and there, obviously a progressive approach, from doing some ground testing or subscale testing to flight testing, that could be one way to go. But this is really critical to success. If we can't validate and point back to validation data that is, as Andrew said, high quality, we don't really have very much of a leg to stand on when we go to the regulatory agency. And number four is similar to this, and that would be full-scale validation, similar to what was done in the 90s with the F-16XL, although we'd like something that's more transport, geometry type. But there are X-planes or the eco-demonstrators where we might be able to have these full-scale flight test type airplanes where we can maybe piggyback onto existing testing that NASA is going through, or even a dedicated flight test vehicle similar to the A320 Victoria project that DLR is doing. And then, crucial again to building confidence in analysis approaches is this comprehensive UQ strategy, and we can leverage previous work with the Department of Energy and their nuclear regulation and things of that sort, where UQ has actually played an important part, and we can adapt that to the aerospace industry. Coming down the home stretch here. So obviously, as I said previously, we can't do it on, no one party can do it on their own. So we have some recommendations for stakeholders, and that's that we need to probably formalize those relationships that we've had with research organizations and industry and regulators, and have some sort of involvement, continued and maybe more in-depth involvement of all members of the stakeholder community. Number two, we need to collaborate to identify appropriate metrics so that we can positively, so that we can move forward with cert by analysis efforts in a way that everybody can understand, and where things can be measured clearly. Number three, this is to encourage blind evaluation of analysis tools. So the FAA it's a lot more convincing when you go to the FAA and you say, we had this one set of data, we put together a process, we tweaked it and we calibrated it, and we, whatever words you want to use, we made it, and we think it's the best process that we can come to. And then we had this other set of data, which was very similar to the first, but not exactly the same. And we put it through our process. And after we put it through our process, then we looked at the results of the experimental data and the results of the analytical data. And here's how different they were, and here's the confidence we have in both sources of data. And if we present that sort of thing to the FAA, that's a very convincing story. And so this is the sort of thing that we can do to help build confidence in analysis for certification. And finally, certification by analysis will require orders of magnitude greater resources in HPC. And NASA and the Department of Energy, they've got some really, cutting edge computing facilities, and maybe we can use those to develop the processes, or we can use those to accelerate the technology development. But ultimately, the manufacturers, the ones who are going to be using this for analysis, they're going to have to make some investments, either developing their own HPCs or upgrading them, or maybe moving to commercial providers, cloud computing or whatever that might be in the future. So we're all going to have to work together to be able to get the analysis capability to the level where it can be used for certification. So in conclusion, certification's really, it's a hard problem, and we're going to be working on it for quite a while, but the benefits are pretty substantial for both manufacturers and researchers. Being able to substantiate money that's spent on particular research is something that has real value for researchers. So we've developed a roadmap that will help to drive progress and highlight critical needs, and provides a little bit of measurement throughout the years where we can see, are we on track? Are we falling away? Where do we need to adjust? So that provides sort of a line in the sand that everybody can look at and work off of. And then if we're going to be successful, we really need to work together, and it's going to be a long period of time. It's see the first element, it's challenging and complex. So it can be done, and I think that in the community there's a fair amount of confidence that at some point it will be done, and depending on how we provide our how we use our resources, it can be done quicker, or it'll take a little longer. So I think that's all I have. Just some acknowledgements. A lot of people provided input from a lot of different areas, people from Airbus, NASA, and then various other people within Boeing and Pratt & Whitney community. So I don't know if there are any time for questions, but that's all at the end of my prepared remarks, at least.
Okay, just thank you very much for that, Timothy. That was very, very informative. And does anyone have any questions? Guess you did a great job explaining that, Timothy.
Yeah, either that or everybody's ready for dinner. So.
Well, thank you very much.
Yes, thank you.
All right. Well, thank you to Melissa for chairing the session, and to our 3 excellent speakers. I ask you to join me in a virtual round of applause for Timothy, Andrew, and Eric. So great job, guys. And thank you to everyone for sticking around to the end of the day. So tomorrow, our DataWorks Day 2 starts promptly at 8:45 a.m. Eastern. You can find the full agenda on our website. We're doing 2 concurrent sessions, session A and session B, just like today. So with that, I will let you go have dinner. And thanks again for coming. And we'll see you tomorrow morning.